Morning, everyone. So we are going to be finishing off our study in momentum in this lesson here. So far, we've been learning momentum as this tendency to stay in motion. It is a vector quantity that has the same direction as velocity. Momentum is defined as going to be the multiplication between mass times velocity, slightly scaled up form by mass. The units so far we've seen for momentum are, it can be in kilogram meter per second, or especially when we got to the impulse formula that changed momentum, we also saw that the units can equivalently be written Newton times seconds. Both units are perfectly fine. Momentum we knew was a conserved quantity, so the physics throughout the section has always been P in has to equal to P out. All the momentum at the beginning has to be conserved by the time all the momentum is coming out. Even though for any given object you might have an impulse, let's say the impulse on the first object is mass times its change in velocity, so this is one way of writing that formula. Even though the momentum of one object might actually, I lost tendency to stay in motion, that's because the other object that I collided with, let's say delta P2, this one here actually has changed enough to be equal and opposite to make sure your momentum overall is still conserved. Especially when we started working to two-dimensional problems, you started needing to break it up between x and y. We basically had expressions, so in the x direction, the sum of the momentum, you can call it px in, had to be the sum of the momentum px out. And similarly, for the y-axis here, the py in has to equal to the py out. So we did that as a sort of conservation momentum kind of problem. I'm just going to quickly sketch over some of the two-dimensional setups that we've done so far, and then we just have one last one to go over for today. First one that we did was a conservation style problem. I'm not going to fully do a numbered question with you here, but for conservation, we had a bomb, or it could be a plate that's just sitting there. As the bomb explodes into multiple fragments, we initially had some momentum. Maybe the momentum was at rest right now, 0 kilogram meter per second. And maybe this one here fractures into a couple different pieces. One piece goes this way, one piece goes this way. So far, I've only done 3 pieces with you. It could be 4, it could be 5, and whatnot. It's just a little bit more work. Basically, you're going to say, well, P in equals P out in the x direction. All these pieces here, the momentum of this piece, px, px, and px, has to cancel out. The momentum of the y piece, this part going up, and this part going down, that part also has to cancel out so that the total momentum actually ends up being 0. That's the conservation style problem. There were no collisions, there was no before and after. The second style question that we did was a vector addition kind of problem. This is the one where we had a plane that was actually traveling in a certain direction. It was getting blown by the wind. Doesn't matter which way the wind is going. And we end up having to just, take this first vector, make sure vectors are adding head to tail, and basically giving you this leftover. This is my overall momentum. This is my P total. This one here is just an addition problem. This is not a P in equals P out. This is just a pure, just like we did it in chapter 1. Just find the x and y components of the first one, find the x and y components of the second one, add the negatives as we need. Let's say left is going to be negative. Implies here total we're still going negative, and we're just going to find what the hypotenuse is. So just be careful for that particular one. There's no conservation involved. We threw over to a quick impulse question. Especially in 2D, it gets to be a little challenging. This one here, we start from the definition. The impulse is given by the PF minus the PI. We had rearranged that a little bit here. If I wanted to move it over, if I just wanted to find, let's say, the PF, that was given by the impulse plus the PI. Right? So that part there should make sense. I would initially be going at this momentum. Were my impulse equal to 0, my final momentum would be exactly the same. But because my impulse here implies that there's actually a change in momentum, depending on how big that change is, that's going to rescale my PI term and actually give me a new PF. In the problem that we did, it was a vector addition question. We would have taken the PI arrow, that's my starting momentum. I don't care which way you actually end up hitting it, the delta P, you have to break up the x and y, figure out those components. But because that there is actually a change, it actually changes your starting momentum into the final momentum. Eventually, it is just a vector addition question like we just did. Pi plus, even though one term we call it delta P, and we actually end up with PF. This is the last question here, which is back to our collision style problems. The physics is exactly identical. It's going to be P in equals to P out. And all we're going to do here is we're going to, again, because it's 2 dimensions, study the x separately from studying the y. Let's start off fairly simple here. Let's imagine this is a top view problem. So I'm in a helicopter and I'm looking downwards. We have two skaters. One skater is here. He's a 50 kilogram person and he's skating 10 meters per second. He happens to be going perfectly east. The other skater here, maybe we're playing hockey. They're both sort of skating for the puck here. Unfortunately, the other skater here, he's 60 kilograms and he's going slightly slower, let's say 8 meters per second, but that direction there is just purely north. They're going to unfortunately collide together. Again, just like any collision problem, I need to tell you something about what happens afterwards. Is it elastic? Is it inelastic? In this question, let's just pretend the collision is perfectly inelastic. If you remember, for inelastic, it means it sticks together. They're going to travel off as one combined mass, okay? I can do 50 plus 60. I know they're going to travel off as 110. Just looking at this number, our brains do this very well, conservation of momentum. We would imagine that it zips off somewhere in that direction. Somewhere northeasterly. I just want to know what is its momentum total. Again, because this is a XY kind of system, I want to deal with the X and the Y separately, although the momentum conservation formula is still the same. All the momentum at before has to be conserved with all the momentum afterwards. So let's take a look at the X direction. At first, I have two objects. So I'm going to have a M1V1 for the 50 kilogram plus the M2V2. These ones here are going to be X because these are horizontal. Afterwards, I only have one object. I could call it M3, but I've already done it for you there. This is just going to be a combination between M1 and M2. They're going to travel off at some velocity. So far, just doing it horizontally, that's going to give me the horizontal velocity. So let's try it out here. I'm a 50 kilogram object. The velocity is 10 meters per second. In the X direction, even though this one here is currently going in the north, is 8 meters per second, it's not going left or right. So when I then multiply it by 90, it's actually 0 in the horizontal direction. This guy is going pure north. He's not going east or west. So that one there is a 0. Even though they're going to get tangled up and they're going to be 110 kilogram together, we're going to figure out what the Vx is afterwards. So let's just punch it through here. We're going to have 50 times 10, which is 500. This one here so far is contributing no momentum. This gives you 110 Vx. Therefore, the velocity in the X direction, 500 divided by 110, gives me 4.5 meters per second. Right? So that one there is the final velocity. In the X direction, let's do a similar calculation, but let's do it in the Y direction. Again, I had two objects at the beginning, but this is going to be V1Y. M2V2Y is equal to M1 plus M2 Vy. Right? So punching your way through here again, we have a 50 kilogram. This one was going east. He wasn't going northwardly or southwardly, so this is actually 0 in the vertical direction. Whereas the Y person, 60 kilograms, and we're going to be traveling at 8 meters per second. This time it is northward. We travel off as 110. What's my vertical velocity going ahead? The first guy gave you no up or down momentum. The second guy, 60 times 8, gives you 480. And therefore we have, this is equal to 110 Vy. The Vy is 480 divided by 110. Gives me here 4.4 meters per second. Again, coincidentally, these are very close together. There's no reason that these ones here have to be very close. In the end, the velocity, I knew it was going to be sort of northeasterly. I could find momentum, but seeing as I already have divided the 110, I can find the total velocity. I can say if in the X direction, I'm still going 4.5 meters per second, and in the Y direction, I happen to be going 4.4 meters per second. What is my total combined momentum? Let's find that hypotenuse there. So V is equal to the root of 4.5 squared and 4.4 squared. Right, so punches in 4.5 squared plus 4.4 squared. This gives me here 6.3. Make sure 2 or 3 sig figs with the units meter per second. And then because velocity is a vector, we have theta. So this is going to be the inverse tan, opposite over adjacent, 4.4 divided by 4.5. Inverse tan divided by 4.5 gives you here 44 degrees. And this one here is the north of east direction. All right. So that one there's velocity. Let's say they actually did ask you for momentum. We can just go straight back to your formula. Because momentum is a vector in the same direction of velocity, all I need to do is take the velocity that I know, multiply by the mass, in this case it's the two players together, and that would actually give you the momentum. One key importance here is it's momentum that's conserved, it's not velocity. I can't just look at this. I can't just be like, oh, 10 meter per second east. That means later on 10 meter per second. It's not just the 10. It's the 10 times 50. You have 500 tendency to go east. That 500 needs to be conserved going east, not necessarily the 10, because we're actually a slightly different mass after the collision. So I'm going to take that mass here. I'm 110 kilograms. Let's multiply it by the 6.3. I know this is at some random diagonal direction, but I'm just going to scale it up here. The mass doesn't change any direction. 110 divided by 6.3, give or take a little bit of rounding, I'm getting 693. And again, make sure you have units to this here, kilogram meter per second. That's my tendency to stay in motion. Direction-wise is exactly the same direction as velocity. That's my tendency to slide off in the northeast. Right? So hopefully that example makes sense for you here. I'm going to show you the one last spin-off of it here. What if these two skaters here weren't coming in purely X, purely Y? What if they actually came in at an angle? This one here comes in at an angle. What if they end up going off at an angle? We'll see how that question looks. So let's just try this out here. Just as an example here. Let's do our first skater. Let's do 40 kilograms, a little bit lighter. He's going to come in at, let's make the numbers a little bit bigger. So 15 meter per second. Let's make the angle here 20 degrees. He's going to collide with another skater, also skating for the puck. Okay, it's like a hockey collision here. Let's say this one here is a little bit lighter of a mass. Let's say 20 kilogram. He's only going at 12 meter per second. I'm going to give you this angle instead. So this angle here, let's make it 60 degrees. We're going to do this twice. First setup, when I tell you after the collision. Part A, let's pretend that it's inelastic just like it was before. And let's figure out how much do those combined masses leave with. Right? We'll come back in part B. If I specify one of the objects go off in some direction, we can figure out what the other guy did. So part A of this question here, but we'll use the same numbers. We'll take this one here. I would first calculate momentum. This first arrow is going to be 40 times 15. 40 times 15 gives you 600 tendency to stay in motion. That's at 20 degrees. When I go down and to the right, I'm going down and I'm going right. So this is going to be my P1y, my P1x. Let's just derive those here. P1y is going to be the hypotenuse, cosine of 20. P1x is going to be 600, the sine of 20. 600, make sure you're in degree mode again. This is equal to 564. 600 sine of 20 gives you 205. So that's P1y, P1x. Right, that's breaking up. Instead of this annoying diagonal, I can think about, oh, it's just going downwards. Down is negative, so I'm going to come along and I'm going to put that negative there. P1x is horizontal, so that's perfectly fine. Similarly here with the other skater, I know the mass and I know the velocity. I'm going to multiply those two first. So 20 times 12. This guy here has less tendency to stay in motion. It's 240. I'm actually going to put that number up above here. So 240 tendency to stay in motion. It's at an angle of 60 degrees. I'm going to call this here P2x. It's the horizontal part going to the right. This one here is P2y. P2x is equal to 240 cosine of 60. P2y is equal to 240 sine of 60. So 240 cos 60 gives me 120. 240 sine of 60 gives me 208. I don't need to change any negatives because this is positive and this is positive. Awesome. Careful, this is not a vector addition question. It's not take this skater and then add the other skater. This is a conservation problem. This is a collision problem. What I'm saying is the total momentum in, we know it eventually it's going to be the 40 kilograms and 20 kilograms mixed up. He's going to be a 60 kilogram. I want to know sort of which trajectory he sort of leaves at. I don't necessarily know he ends up going downwards. That part there was really going to depend on the angles and these numbers, but we're trying to figure out what's his total momentum here. So let's just try it out here. In the x direction, my P in has to equal to P out. So if I take P1x, the horizontal velocity of the first guy, plus P2x, the horizontal velocity of the second guy, this has to equal to P1x, actually sorry, they're combined, so P total of both skaters. I'm going to take just their x components. First guy had 205, the other guy had 120. If I have a combined 205 and then I have a 120, that means my total momentum that this 60 kilogram combined mass has to have, the total momentum at least in the x direction, P total x, 120, give or take a little bit of rounding again. I'm getting, oh, sorry, is it 205 and 120? 205. Gives me here 325, also in the forwards momentum, right? Shouldn't surprise you. First guy had an X momentum. The other guy also has an X momentum. To conserve that, overall, this guy still has an X momentum that's positive. What about in the Y direction? Also, the physics is simple. P in equals P out, but we're going to go P1Y plus P2Y gives you your total in the vertical direction. We're going to add these two up then. P1Y is going to be a negative 564 because that one was actually going southward. The other guy was only trying to go upwards at an upwards of 208 plus 208. That gives me my P total Y. P total Y is 208 minus 564. Gives me here negative 356. And there I have my answer. Eventually, when they get mixed up, tangled as a 60 kilogram object, they will still have a tendency to go 325 in the rightward direction, going to the west. And then this negative in the vertical tells me it's going south. It's a little bit bigger, so it's going to be 356. I know that negative just implies south. So once I actually put down the arrow is pointing south, there's no point in putting that negative anymore. You can probably finish that out for yourself here. You're just trying to find the momentum and this theta here. Momentum will be through just Pythagoras, and the theta will be using inverse tan. Right? So I'll allow you to solve that out there. I'm going to finish off with part B of the question here. So part B of the question, what we're going to do is we're going to take exactly the same starting conditions. We're going to take the 40 kilograms, 20 kilograms, and all that. But unlike this one where I told you that it's actually inelastic, I'm going to actually give you how it bounces off. We're not going to fully do it elastic because that algebra is going to be a little bit crazy. But what if I told you one of the directions that one of the skaters leaves at, it's still going to be P in equals P out, but instead of becoming one combined mass, I'm going to still have a P1 X final, P2 X final, whatever's not taken off by my first skater, the other skater has to take with it. So let me just recopy out these numbers here. Same starting numbers because you have some familiarity with it. 40 kilograms, it was traveling at 15. The angle of it was 20 degrees. The green skater here is 20 kilograms traveling at 12. 20 kilograms traveling at 12 meters per second. The angle is 60 degrees. They still collide in the same fashion. Momentum is still going to be conserved. But this time, this is going to be part B of the question. Instead of telling you that this one here is actually going to be inelastic and they stick together, I'm going to tell you that after the bump, they actually don't get interlocked, but this first skater ends up skating off. Let's say he ends up going off, making up numbers here. Let's say he goes off at 8 meters per second, and he has a slight angle of, let's make that 60 degrees, right? So what's happening here is these two skaters are skating for the puck. They're going to collide together. I know momentum is going to be conserved, but the question here is, if the first skater ends up bouncing off of that trajectory, where's the other skater going to go? Is the other skater going to bounce back this way? Is the other skater going to bounce back this way? I want to know the velocity of the other skater. So let's pretend we were given that question here. The question will be worded here. Calculate the velocity of, I'm just going to call him the green skater as drawn on my diagram, after the collision. And the only difference this time is we were told that the blue skater is actually traveling off at some other velocity. So far, I've already broken up a couple vectors. So our P1, remember we had done 40 times 15. We had done that, it's 600. Let me actually just copy these values down here. So we have 600 as my first momentum. When you broke it down, it was X was 205. The Y was a negative 564. That's why it was downwards. That's P1. Our P2, once I multiplied 20 times 12, this gave you here a total momentum, a total hypotenuse of 240. The X and Y, the X was actually 120. The Y was actually 208. So I actually have a lot of it done already. Right? If this was just given as its own question, you'd still do that first part. First trick here is to find the momenta, P1 and P2, because remember it's conservation of momenta, not velocity. This time, because after the collision, they don't just intertwine together and inelastically collide, this time here I actually have 1/3 vector. And what I'm going to do is exactly the same. I'm going to call this vector here, this is now after the collision. I'm going to call this one here P1 final. And what I'm told, I'm assuming the mass is still 40 kilograms. Because he's now traveling only 8 meters per second as opposed to the 15, I'm going to go 40 times 8. This gives me a hypotenuse of 320. Again, unfortunately, I have an angle to this. Anytime you have angles and vectors, you have to break down components. Let's figure out the P1 final x, P1 final y. Let's do that right beside here. 320 cos of 60. The other one is going to be 320 sine of 60. 320 cos 60 gives me here 160. 320 sine of 60 equals 277. Because this one here ends up going down and to the rightwards one is fine, that can stay positive. The downwards one is negative. I'm going to purposely come in and add that negative there. And now I'm ready to do my final calculation here. I want to just keep emphasizing the physics is just P in equals P out. At the beginning, I had two momenta. At the beginning, I had P1x, which was 205. That was supposed to be added to P2x, which was our 120. P2x is equal to 120. In total, that gave me earlier that 300 something value. But this time, even after the collision, I also have two objects. Because I have two objects here, I'm going to have a P1 final x term and a P2 final x term. Our P1 final x term I just calculated. This is this positive 160. Basically what I'm saying here is, yes, in total we had some 300 or so tending to stay in motion. The first object when he leaves, he actually takes with it an extra 160. How much does my green skater need to take away in the x direction? I just solved through the math for you here to make sure the momentum stays conserved, to make sure it's equal before and after. So 205 plus 120, this was supposed to give me a total of 325. That's the number we used earlier. But if the first skater actually takes away 160, 325 minus 160 leaves me 165 for my green skater to take away. That's also positive, and that's also eastward. Let's compare that to the y direction then. The y direction, again, the physics is P in equals P out. I have my numbers here. My P1y was a negative 564. He was actually going southward. My green skater was going upwards. He's trying to transition the momentum. He's trying to give it some upwards momentum. Let's call that P2y. Again, my first skater, this time he actually leaves with a negative 277. So P1 final y is a negative 277. And then we're figuring out, for momentum to be conserved, how much should this green skater take away with it? Okay. So practically the same thing, but I'm just figuring out what is this unknown P2Fy. If I take 208 and I minus 564, that was my earlier, I had gotten negative 356. This has to equal to the negative 277. If the first skater already takes with it negative 277, I just add that 277 over, and therefore I get P2Fy is negative 356 plus 277 equals to negative 79, and that's going to be your momentum in the vertical direction. And now, again, we have an x and y component. This is for the green skater. At first, I didn't take out a protractor. I didn't take out actual numbers to scale these arrows. But knowing these two numbers, this green skater has to still have an x momentum of 165. That was eastward. And in this case here, he still also has to be going negative. Basically, he's getting bulldozed by this heavier skater and fast skater here. He still actually needs to go off at a little bit. Negative 79, the negative just means downwards. So then I can do my Pythagoras here. Let's find the P of the skater in this setup and the theta. I'll finish this one off for you here. 165 squared and 79 squared. And the theta is the inverse tan of 79 over 165. The root of 165 squared plus 79 squared. This gives me here 183. Make sure you have units 2 or 3 sig figs. And then the inverse tan 79 divided by 165. And this would give me the direction 26 degrees. So if you look just sort of roughly at those numbers here, what's happened is we had the blue skater skating for the puck. We had the green skater skating for the puck. This time they collided. We still use the same physics, momentum conservation. This time the blue skater ended off sort of bouncing off at this direction, but because this guy was heavier and this guy had a faster speed, the green skater, even after the momentum, also travels with it, right? And that's just sort of a completion of studying momentum conservation. We saw any time we had vectors, we had to break up the x and y components, and then Pythagoras comes along and saves the day to figure out what's the overall size, and then the angle is with inverse tan. They may ask you to calculate velocity. Remember, it's fairly easy. P is supposed to be m times v. Your velocity can just scale the mass term back out. This time I have a tendency to go 183 in this 26-degree angle. This one will be worded south of east. I would then divide it by my mass. The mass of the skater here, let me just double check. The green skater here was 20 kilograms of mass. So we're going to divide it by 20. And this gives us here 183 divided 20 gives me 9.2 meters per second. The direction is going to be exactly the same as momentum. It's also going to be 26 degrees south of east. Now, just one caution before I leave you for today here. The caution is, you'll notice in all this physics, I've emphasized this multiple times already, the physics is momentum is conserved. Sometimes people, when given this question, they see a bunch of arrows, they're ready to do the components, they're ready to say, oh, 15, let's break up the Vy and the Vx. Oh, this one here is 12, the Vx and the Vy. You can still break out the components, no problem, but when it comes time to actually do your calculations, make sure it's actually momentum that you're trying to conserve. It's actually having scaled in the mass that's being conserved. Don't just come along and be like v1x plus v2x. The velocities add up to this, so this has to be the final velocities. Velocity is definitely not conserved, especially when the objects have totally different masses. That's why I generally find it's easier, because we know it's going to be conservation momentum, do a m times v at the really beginning. Make sure the arrows that you have are already momenta arrow. And anytime you need to find velocity, like we did at this very end here, if you know what the momentum is, this tendency is, just double check what the mass is. Oh, this is just the mass of the green skater. He bounced off. You divide it by the mass of the green skater, and this leaves you with the velocity. Okay. So that wraps up our momentum chapter. I'm going to assign for you the two-dimensional sort of video inquiry project, and that'll help you flesh out some of these concepts. After this lesson here, we're going to be switching over into our next chapter, which is on energy. Also not a very long chapter. We'll probably do one big test with momentum and energy together. Thanks, guys. If you have any questions, just let me know. Take care.